formal charge. Okay, formal charge, that's the formula of. And now, okay, so you come out with two structure. For example, this one, you got these two kind of structure, either single bond or double bond. Okay, so how do you know which one is correct? So we have to use the formal charge formula in order to know which one is correct. So valence, first thing first, you have to calculate valence electron of each, of sulfur, of oxygen, of hydrogen. Okay, and then sulfur, hydrogen. Okay, so oxygen might be bonded to one to oxygen might be bonded to S or to D structure. Alright. Okay, so oxygen might be bonded to this one. Okay, this one or this one. OH or OS. Alright. Okay. Let's calculate one by one. Okay. First thing first, we calculate for formal charge of the center first, of the sulfur. Okay, so sulfur is 6 electron valence. 1, 2, 3, 4, 5, 6. Okay, that's its valence electron of sulfur. Minus how much it has bonded. Bond to atom, it bond here 1, 2, 3, 4. Okay, it has 4 bonded electron. Plus with unshared electron. There is no unshared electron. Everything has been shared. Okay. Alright. So everything has been shared. Okay. Why is it? It's become 6. Okay. So because of we have 2 plus. So means that we don't need 2 to others. Okay. Alright. So that's why it's just remaining 6. Alright. So that one that will remain 6 minus 4 is equal to 2. That's its formal charge for sulfur. Right, so that's why you write 2 here, 2 plus 2 here. Okay, so next is formal charge for hydrogen. Hydrogen, we have formal charge for hydrogen. Hydrogen, luckily it just bond to oxygen here, and then it just bond to oxygen here. Okay, so hydrogen is just valence electron number is 1, and then bond to atom. Okay, only 1 here. 1 bonded to atom. Okay, and then unshared electron, there's nothing that has not been shared, so everything has been shared. So 1 minus 1 is equal to 0. Formal charge for hydrogen is 0. You can write here 0. Okay, right. Then formal charge of the oxygen. Formal charge of the oxygen in the S structure. Okay, in the sulfur structure. Alright. Okay, so this one. So this one, oxygen. Oxygen, we look at the oxygen here first. Okay, we look at the oxygen here. Let's share with the S. 1, 2, 3. 1, 2, 3. They are similar. Alright. 1, 2. Okay. So, valence electron of oxygen is 6. And then bond to atom is 1 and 2. Okay, 2, and then plus unshared electron. How many unshared electron? Unshared electron is 1, 2, 3. Okay, so this one first. Unshared electron is 6. Okay, 6. Alright, so 6. Repeat for sulfur. So we delete everything. Okay, so now we're going to compare for on this part. Okay, formal charge of the oxygen on this part and also this part, they are similar. Alright, so let's see on that. So electron valence is 6 minus with bonding, only 1 bonding here, 1 bonding here, so same as 1. And then we focus on one side. We focus on this side, for example. Alright, and then unshared electron is 6. So 6 minus 7 is equal to minus 1. Okay, so now okay, so we delete this one. We're gonna, okay, so now oxygen on this part. Right, oxygen on this part. So valence electron of oxygen is 6. Okay, minus with how many bonding that it makes? It make 1 here and it make 1 here, so 2. 2, and then plus how many unshared electron? Unshared electron is 2, 4, 4. So 6 minus 6 is equal to 0. So this one is 0. So this one is 0 as well. Hydrogen just now is 0. So this is 0. Alright. So basically when we have this kind of formal charge, okay, minus 1, positive 2, positive 1. So now we have to compare with structure number 2. Which one is close to 0 or lesser number? That will be the correct structure lah. Alright, so we do one by one. Formal charge for sulfur first. So sulfur 16. So electron valence is 6. Okay. And then minus bond to the atom. 1, 2, 3, 4, 5, 6 bonded to the atom, and unshared electron is 0. So 6 minus 6 is equal to 0. Alright, so next is formal charge. You have to calculate everything. Formal charge of the hydrogen here is similar like here. So we just calculate on one side. So hydrogen 1, it has a bond to atom only 1. This one. Alright, and then unbonded unshared electron nothing. So 1 minus 1 is equal to 0. So settle on that. So this is 0 for S. This is 0 for hydrogen as well. So next we calculate formal charge of oxygen for center S. S for S and bonded to the S. Alright, so this one. Oxygen has 6 electron, valence electron, but now bond to the atom is 1, 2. So 2 has bonded to the atom. Unshared electron is 2, 2, another 2. So here we have 4. Okay, 4. Okay, so 2 minus 2, 6 minus 2 plus 4 is equal to 0 as well for D. Okay, for another one, this one. Okay, so alright. So this one for D orbital. Alright, so we can share this one. Alright, so basically 6 electron valence minus bond to the atom is 1 to the left, 1 to the right. Okay, so 2 plus with 4 unshared electrons, so still equal to 0. So basically this all formal charge all are near to 0. So this one is much more appropriate to be accepted compared to structure 1. Okay, that is how we do on electron valence. When several Lewis structure are possible, we always choose the smallest formal charge because that is more stable and most preferred. Okay, more stable Lewis structure, it has lowest possible formal charge. For example, if near to 1 or 0, that's better. So any negative formal charge on most electronegative elements. So next is VSEPR theory. VSEPR theory is used to construct a molecular shape from Lewis structure. Okay, so VSEPR stands for valence shell electron pair repulsion. VSEPR is a theory for basic principle. Each group of valence electron around the center is located as far away from as possible to minimize the repulsion. So in order of strength, it has electron pair repulsion as this lone pair with lone pair, it has much more stronger compared to lone pair with bonding pair, and this type of bonding is much more stronger than this is bonding. You may see which one is lone pair. Alright, so you have two lone pair, you have greater repulsion compared to, sorry, you have the lower repulsion, but you have strength. Your strength is much more better compared to this one. Okay, if you look at this one, bonding pair versus bonding pair, it's just normal bonding pair, so it just stretch and repel to each other with a longer angle. Okay, but the bonding is less strength, the mostly strength. But if you have lone pair versus bonding repulsion, you have one lone pair, basically you're going to repel. you tutup sikit. Alright, so okay, because of lone pair ini akan terus repel the angle. Okay, that's why it's going to shrink a bit. Alright, to 107. This is the same structure, but when you have another two lone pair, so basically you're going to repel more. That's why this is much more stronger. You're going to repel more, so, and then the angle going to be reduced again. So now we have electron group repulsion and molecular shape. So these are the most common VSEPR shape that you must know. We have linear, we have trigonal planar, we have tetrahedral, trigonal bipyramidal, and also octahedral. So you must know this one. Linear is like this with 180, trigonal planar is 120 angle, tetrahedral is 109.5, trigonal bipyramidal with 90 and 120, while octahedral it has both 90 here and 90 here. So VSEPR is based on a formula defined by relative position of atomic nuclei. So basically, electron valence can be bonding or non-bonding. The same electron arrangement can be rise different molecular shape. So this is the formula AXMEN, where A is the central atom, X is the surrounding atom, okay, and then E is the non-bonding electron valence, M is the number, how many number of X will be exist there, how many number of E will be bonding there. So for example, this one, single line is AX2. AX2, so A is the center, XU, you got 2X. For example, like CS2, HCN, or BF2. Okay, HCN is also considered as linear. Right, so it has 180 degrees. This has to be trigonal planar, it has 120. Formula is AX3. Okay, AX3, A in the center, X point out for 120 degrees each. Okay, and then we have AX2E. E is the lone pair. Alright, so for example, we have like SO2, E03, PbCl2, SMBr2. So the shape is band. Okay, right. Then we have tetrahedral with 109.5. 109.5 here. Okay, here 109.5. For example, CH4, SiCl4, SO4, ClO4. This is for AX4. But if you have this one, AX3E, so bonded with 3A center metal, bonded with X3, but then it has one lone pair. So this is known as trigonal pyramidal. Okay, if you have AX2, AX2E2 means that you have two lone pair, XU just two with band. This is a band shape, Alright, this is trigonal pyramidal. So fluid structure and molecular shape is same, For example, CCl2F2 is the same as this arrangement. It doesn't matter where you put the Cl. Okay, for example, your orange is the Cl. Okay, fluorine is the green one. You can put the green one next to each other, and Cl will be here. It's okay. They are similar. Okay, angle is similar. Okay, for trigonal pyramidal, the formula is AX5. So it has angle of 90 and 120 degrees here and 120 at this part, and also this part. Alright, that is 120. For example, PCl5, SF5, SOF4. Okay, if you have AX2E, you got one lone pair. You deduct from AX5, then it become AX4E. Alright, so the rest are seesaw. So straight macam tu, dia ada seesaw. Right, these are example of seesaw. And then if you deduct lagi dua, so dua lone pair, jadi tinggal AX3 E2, so that will become T shape. For example, like ClF3. If you deduct 3, become 3 lone pair, so AX2 E3, so you got linear. Okay, so we didn't count the shape based on this. We didn't count the shape based on the lone pair, but we just look at on the X dia siapa. Okay, ni X dia. That's why T shape. This is linear straight saja. Ini X dia dalam bentuk seesaw macam tu, Alright, okay. Alright, ni X dia dalam bentuk piramidal Right. Okay, octahedral 6. Octahedral means that it has 6 X, so AX 6. Okay, so it has 19, 19, 19 here, 19 here, and everywhere 19. These are example. Okay, if you deduct 1 with the lone pair, you got now AX5 E1. So it becomes square pyramidal because it has 4 atas ni. Okay, so it becomes square pyramidal. If you deduct 2 for lone pair, so it become AX2E2. So it becomes square planar. Nampak ni shape dia macam square planar kan? This is a square planar Alright. So we continue next slide.